All right, recording is rolling. Welcome to a brand new week, Monday, September 25th. All right, so last time I saw you guys back on Friday, we solved a few outwits. So I have an outwit as a starter question here. Actually, there's a pair of questions, right? So if I got 4 kilograms versus 5 kilograms, can you figure out what's the acceleration? You might word that like what's the downward acceleration of the large mass, something like that, right? And furthermore, what is the tension connecting those two masses, right? Got some Paul Hewitt demos lined up for you guys, and then we'll solve a couple of textbook puzzles to close out the class today. And then we'll do some more textbook puzzles tomorrow. This is due on Friday, but we'll be done by then. I did write you guys this next quiz over the weekend, so I don't have it for you guys right now. I need to print it out, but it was due pretty soon, probably tomorrow. Be another one of these take-home quizzes. Right? Have a few days to do that. All right. See, they happen to solve this by now. Right, what's the acceleration? What's the tension? Right. Right, so let's go ahead and do this. Now, there are different ways to solve this. Let's start by looking at big picture. I'm just going to copy that picture pretty much. So I've got 5 kilograms right here. I've got 4 kilograms right there, something like that. Okay. So big picture is maybe I could start thinking like, I wonder where like some reasonable values or maybe compare to like some boundary conditions for what the answer could be. What is the acceleration? Acceleration. Okay. Okay. So the fact that these masses are pretty close to each other, I suppose I have like a scale. And at one extreme, I have like 0 meters per second squared. And at the other extreme, I have pure free fall, g, like 10 meters per second squared. Right? Where do you think this is going to land? Closer to 0 or closer to g? What do you guys think? They're really close to each other. 4 versus 5 kilograms. I think it's probably somewhere right there. You guys think? That's what I'm thinking too, right? The follow-up question is what's the tension in the string? Maybe I'll get free body diagram going. Is what is this weight pulling down right here? How many newtons? About 50 newtons, right? Okay. Maybe I'll call that here. Let's call this mass A, mass B. Okay. So mass B, G, yeah, 50 newtons. Right? How much force down right here? Like 40 newtons. Okay. Okay. So about 40 newtons versus 50 newtons. Right. Now those are the external forces, right? Gravitational weights. Right? Those are the main ones I care about. But there is a question of something to do with tension. So let's draw tension in here too. Okay. Do you guys think that tension would be the same on both these blocks? Like whatever the tension force is right here. You guys think it's the same tension force right here? Yeah. One string has one tension in it, right? As long as this pulley is like massless, frictionless, nothing crazy going on. Right? Also, do you guys think this tension force is like a Goldilocks force? Do you guys think it's larger than 40 newtons, but smaller than 50 newtons? So that there could be a net force upward on the small guy and a net force downward on the large guy? Okay, okay, you guys think that? Okay, so yeah, this is all just big picture framing, but we need some way to actually solve it and get some actual numbers, numerical answers. Okay. And back last week, I was telling you guys there's like 2 main approaches to solving these. Like there's a micro perspective and a macro perspective. They all lead to the same answer. Okay. Yeah, I'll recap the micro. Did some examples last week with you guys, but then I'll actually take you guys macro through this thing. Okay. The micro way is to set up a system of equations. Okay. So for the free body diagrams. So there's a free body diagram on mass 1. It's got a weight down and a tension up. There's a free body diagram on mass 2, a weight down and a tension up. Okay. And you can apply Newton's second law of motion to each individual block. So here's for mass 1. Well, the difference in those forces is the net force. Up minus down is the net force. Net force drives mass times acceleration just for that specific block. Okay. And the other block, similar story. The weight down minus the tension up drives mass times acceleration for the second block specifically. Okay. Now, between these two, you could set up a system of equations with 2 equations and 2 unknowns, because you would know a number of things. Maybe you know what is mass 1 and what is mass 2, like in my example here, 4 and 5 kilograms. You can know Earth's gravity field, 10 meters per second squared. So the 2 things you would not know that you could solve for are what's acceleration and what's the tension. So you could solve it that way, and the rest would be algebra from there. Okay. Okay. Now the macro approach, which I'm going to walk through with you guys, is to look at this from a systems point of view. Say, well, there's really these 2 external forces, and I'm going to start out by just ignoring this tension force, because tension is just internal to the system. It's just holding everything together, just bonding everything together. But really, the 2 weights, it's a competition between 2 weights that's going to drive the motion. Okay? So those are my external forces. and I can set up Newton's second law of motion from the system's point of view, right? So we got clockwise versus counterclockwise, right? So the difference in the weights, right, would tell something about the net force to drive the system as a whole, right? And the sum of the masses is the total mass that's being moved around, the total inertia, right? Look at that, net force on total mass for the system as a whole, right? So let's try it that way. Right? So I'll say maybe acceleration is of the system, or you could say the downward acceleration of the large block, something like that. Okay? Is, well, we got these two forces competing, clockwise versus counterclockwise. Let's go 50 newtons compared to 40 newtons. So it's like a net force there. Right? And how much mass moved around? Well, we got 5 kilograms plus 4 kilograms. Right? The forces I subtract, forces a vector quantity, and they're fighting each other. The masses I add together, masses are scalar quantities, so just add them all up. Right? So the acceleration is, I got a 10 Newton net force acting on 9 kilograms total mass. Acceleration is 1.11 meter per second squared. Okay. I'm saying acceleration in general. You could say that's the downward acceleration of the large block. You could say that's the upward acceleration of the small block, because they are accelerating opposite directions. They're the same magnitude. They're all tied together with a string. Okay. So, and look at that. Just what I was thinking, right? Remember I said from 0 to 10, it's got to be probably closer to the 0 side. Right. So the other question, though, is what is the tension in the string? Now, if you guys had to just make a ballpark guess, right? Like you're guessing how many jelly beans in the jar. I was like, okay, well, I got a pretty good guess, right? I want to get the closest one. I won the competition. Right? How many newtons do you guys think is probably the tension force? What do you guys think? 46 is a good guess, right? Because it has to be between 40 and 50, right? Having done so many of these over the years, if you average these two weights, like in this case, the average would be like 45. It always ends up being a little bit less than that. Right? So average 2, subtract a little, right? So somewhere there. Right? But if you want to get it exactly, you can set up the free body diagram for either of the blocks. You can focus on either of the blocks and then solve for the tension from there, because we know what the acceleration is. So you just plug that in. I'll do both of them and show you that it comes out to the same number regardless of how you solve it. So from here, let's do this. Put the paper up where you can see it and see my diagram. Okay. So this tension up we're solving for minus this 40 newtons down equals 4 kilogram mass times the acceleration, which we just found to be 1.11 meter per second squared. It looks like up is positive in my case. Oh, I should have said this. I should have said net force on block A is equal to mass of block A times the acceleration. Right? That should have been my first step, right? Got that, and then it pops in like that. Okay. So 4 times 1.11, is that like 4.44? Plus 40. The tension force is 44.4 newtons. There you go. 44. Hey, that is between 40 and 50 newtons, right? Just like that. All right. Okay. Or I could have gotten that also by looking at block B. Now, block B, maybe I'll change the definition of what's positive. Maybe I'll call it down positive this time. Okay? So the net force on block B could be mass B times its acceleration. Okay? Net force on B is, well, I got 50 newtons acting downward in the direction it wants to accelerate, minus the tension force holding it back. Right? There's your net force. Okay. That's going to drive this 5 kilogram block, also 1.11 meters per second squared. Okay. It's like 1.11111. It's like a string of ones. Okay. Let's try this out. If I add over the tension and subtract this over, that means the tension force would be equal to 50 newtons minus 5.5555 newtons, something like that. Okay. 50 minus tension force. Hey, it's the same thing we got before. Look there. It's the same thing. Okay. So you didn't have to do both. You can just do your favorite way, but either way, it's the same answer. Same tension force. Okay. You guys remember that from Friday? All right. All right, we're all warmed up here. All right, so let's switch over, watch some Paul Hewitt. All right, so got a few videos. They cover the bases of Newton's first, second, and third laws. You may have seen one or two of these before. Also, there's some kind of copyright thing, or I assume some kind of copyright protection where I've noticed, and students told me this too, when I play these videos on the Zoom recording doesn't actually record the audio. I don't know why, but all these, oh, okay, thought I had the folder ready. Right. All these videos that you guys see today, they're all in a folder on Google Classroom. If you go back to the first week materials, they're all just in a folder there. Okay, so you can see all of them there too, even if this audio doesn't play up here. Okay, let's get this over. All right, let me get Zoom set up. Got to switch my screen. Sorry, it's a lot of little setup things. Okay, share screen. Here we go. Okay, all righty. Law of inertia, first law of motion. There you go. Object at rest and stay at rest. Law of inertia. Let's look at Newton's second law. Ooh. All right, next one. Bed of nails. Did I show this one to you guys? I saw bed of nails thing. No? Yeah, yes, maybe. It's yes and no. All right. Well, one way or the other. You guys can say it again. How about that? So this has to do with how many guys ever been on a bed of nails? Been on a bed of nails? Been on a bed of nails? Yeah, some of you guys. Okay. Uh, You get to choose. Would you rather be on a bed of nails of 1,000 nails or a bed of like 2 nails? What sounds better? Well, let's go with 1,000, right? Your weight doesn't change. Your weight would be the same on both of the beds, right? But what does change? Yeah, how much air is distributed over, right? Because on 2 nails, it's like, okay, well, each nail's holding half your weight, right? Oh, hey guys, the, your weight's kind of force. Force per cross-sectional area. There's a term for that in physics. It's called what? Pressure. Kind of pounds per square inch pressure, but in this case, would be like Newton per square meter. Yeah, each of those nails has a head with like some cross-sectional area on it, right? Yeah, yeah. Pressure, force per unit area. Yeah. Same with the third law, Newton's third law coming up. Come on here. Here we go. Yeah, same. Newton's third law of motion. It was only one tension in that string. Okay. All right. So you guys, textbook puzzles. Right, back on Friday, we did number 92, which was the last chapter 4 question that I assigned you guys. It's just the circles ones I'm doing. And so let's flip over and do chapter 5. Now, some of these are a little bit out of number order. I was trying to fit as many as I could on a page. But first one I got circled here. Let's do number 98. 98 is what we're doing. We got a street lamp, weighs 150 newtons. Right. Pause right there. What's the mass of that street lamp? Like 15 kilograms, right? But you know what? I think if that street lamp's like hanging in equilibrium, I probably care a lot more about its weight than its mass. So they went ahead and gave us this weight, 150 newtons, supported by 2 wires that are 120 degrees from each other. The tensions on the wires are equal, right? That's a helpful simplification. Show you guys why. Okay? What is the tension in each wire? Right? And there's a follow-up question that says, well, what if you change that angle to 90 degrees? Then what would it be? So let's do the first one first, and then we'll go change the angle and see what happens. So number 98. All right. I'm going to set up a set of Cartesian axes. Okay. Cartesian system. Okay. Let's say the central dot right here is where all 3 wires come together. All 3 wires come together. Okay. So I've got the street light here. I'll make it like a one of these. I don't know. Maybe that's not what they're talking about, but there's some kind of weight. Okay? And that street light is pulling straight down with some force. Okay. fact, they told you what that force was. They said 150 newtons. 150 newtons. Right? Then there's a couple of cables holding it up at 120 degrees away from each other. So let me draw as best I can here. So like that, not like that. Pretty close. It's pretty close. Bam, bam, maybe like that. Okay. All right. Now, okay, they gave you a couple of hints how this is going to play out. They said there's 120 degrees between those two. So there's 120 degrees right there. Okay. Oh, yeah. Yeah. They also said that they're the same tension, which makes me think that there's symmetry going here. There's like vertical axis symmetry, right? So I'm going to label this F sub T like a tension force, and I'm going to label this one also F sub T a tension force. Right? Now, they didn't have to be so nice. They could have made this asymmetrical and call it the left force and the right force, and we'd have to solve for each one. But say, just go ahead and say, same tension, it's symmetrical, right? Guys get that? Right. I do have a poster that looks almost exactly like that. Does that look like that? Right? Okay. We got a weight hanging down, right? And then there's a couple of forces pull off some angle. Now, the principle to set this up is, well, suppose you assign some kind of Cartesian system, maybe the lines with the weight, right? Then you can break these forces into components and say, well, how much up and how much over do they pull? Right? And then the right component and left component have to balance out, have to zero out because of equilibrium. And also everything vertically. So these two upward components have to balance with this weight down. So it zeroes out vertically, right? These are our two conditions. Right, you guys get? Right. Now, side note here, what would it look like if it was not symmetrical? Oh, hey, how about asymmetrical? What if you have like an alpha and a beta, and these tensions were different? So I could call it the left tension and the right tension, right? Left force, right force, right? Right. Well, the framework would still be the same, right? That however much this guy's pulling to the right, this guy's pulling to the left the same amount, so that the force zeroes out horizontally. Okay. And then vertically, well, we got this component acting upward, balance out with this weight pulling downward, so that it zeroes out vertically, right? So it's still the same framework, just gets a little bit more complicated because now you got two unknown tension forces, and you got an alpha and a beta, and you got sines and cosines floating around. But this would be the okay. Is that? There's a little bit more complicated version. Right, here's a simplified version of what we're doing. Right. One change I'm going to make from this poster is instead of going up first and then over, I'm going to go over and up. I actually went back and redesigned this poster too, because if you go up and over, that's a lot of writing in a little confined space here. If I go over and up, then I got more space to write stuff. All right, let's take care of that. So I'm going to break these tensions into components. Say, well, this guy pulling to the left, it's kind of left and kind of up. This guy pulling to the right, or up and to the right. It's kind of right and kind of up, right? But how much? How can I quantify that? Right? Go back to sine and cosine type, right? All right. Well, what you guys do know is that the angle between these two ropes is 120 degrees, right? Oh, speaking of which, I meant to mention this before I broke these into components, right? Let's get a different type look at this. I want to attach a different story to this. I've done this before. Guys, what if we're up in a helicopter, we're looking down aerial view on like three guys playing a three-way tug of war? You guys imagine that? We're up in a helicopter, looking straight down. You guys see three-way tug of war, right? Guys, if this was 120 degrees, what's this angle right here? 120. What's this angle right here? 120. Do you guys see not only vertical axis symmetry, do you guys see actually some radial symmetry, right? They're all same number of degrees between the ropes, right? So if this guy is pulling with 150 newtons this way, what's each of these guys also pulling with so that it has to balance out radially? Yeah, it has to be 150 newtons, right? 150 this way, 150 that way, 150 that way, right? Is that right? Right. So we kind of know what the answer is going to be already from a different point of view, right? But what if it didn't have that radial symmetry or something? So let's figure out these angles. All right. So what is this angle from here to here? Like from this rope to this vertical axis? What's that angle? 60 degrees. Hey, could you guys say what's this angle right here? 60 degrees. Right. What's this angle right here? 30 degrees. Right. And then the same story on the left side, kind of, right? Right. So you can play off the 30 or the 60-degree angle. It's up to you. I'm going to play off this 30-degree angle myself. Right. So whatever the tension force is, if I multiply by cosine of 30 degrees, that's tell me how much to the right this guy's pulling. And similar story on the left. The tension force times cosine of this 30 degrees is how much this guy's pulling to the left. Right. Right. Now I can say these are the same tension force because the boat did say they were the same tension force. Right? it was more complicated, cut the left and the right force. Okay. Right, let's look at vertical. Is this the tension force times sine of 30 degrees? And this is the tension force also times sine of 30 degrees? Like that? How much up each one's pulling? That be true? Right, so you go like that. Right. Okay, so now we got some components. Right? Right. Now let's think about these conditions. I said if you can satisfy these two conditions, you can solve this. So horizontally, everything zeroes out. Vertically, everything zeroes out. Right. So horizontally, these two zero out. Vertically, these two up balance with this weight down. Maybe something like that. It's let's do some math on this side of the page. So let's start with the horizontal stuff. Some of the forces horizontally goes to zero. 0 newtons, I guess. Right. Now what? Ooh, well, that's Ft cosine 30 to the right, Ft cosine 30 to the left. So the tension force cosine of 30 degrees to the right minus the tension force cosine 30 degrees to the left. I'm saying minus because right versus left, right? Right. That's 0, like that, right? Well, that's kind of a dead end, right? Because it doesn't matter what the tension force is. Anything minus itself is just 0 anyway, right? Although, if you didn't 100% know that they were the same tension, but you did know the geometry, then you call it force left and force right. I guess what this could be good for is confirming that they would be the same force, right? Given that particular geometry. Right? So anyway, that aside, let's look at what's going on vertically, because they definitely know something to do with this weight right here is going to lead to the answer. Some of the forces vertically goes to 0 newtons too, right? That's the other condition, right? So what's that look like? Well, I got these two guys pulling up. I got this guy pulling down. So let's call the tension force times sine of 30 degrees plus another tension force sine 30 degrees, also pulling up there, right? Minus the 150 newtons down is equal to 0 newtons, right? Isn't that in the vertical? These two guys up, this guy down, have to zero up, just like that. Okay. Does anybody happen to remember what is sine of 30 degrees? Does anybody know? What is sine of 30 degrees? Sine of 30 degrees. It's probably a good one to know. Is it half? Half, right? So here, half of the tension force there plus half of the tension force there. I'll go ahead and take this 150 newtons and slide that over. Equals 150 newtons. Bam. Okay. Oh, half tension plus half tension. Hey, that's the full tension right there. Equals 150 newtons, right? And we were thinking about the radial symmetry of this problem. We said that had to be the answer anyway, right? Before I started doing any of this component analysis, right? Right? Is that true? Okay, you guys get there? So the next question is, that was question A. This was 98A. Right? 98B said, well, what if you take this, what used to be 120 degree angle between them, and you make it like 90 degrees? Which makes me think of a lab I gave you guys a few weeks back. You guys remember the 10 mini labs that you guys had spring scales? Yeah, you guys remember that? Right. Well, here, maybe let's get the poster version of this. Okay. Now, as long as it's all symmetrical, it could be some version of this one, all right? Okay. So suppose this is 150 newtons straight down. So let's play around with the angle. Think what could go on with that? Right. Let's go on with these spring scales. If it's 150 newtons straight down, if you pull both scales exactly vertical and it's symmetrical, what is the force in each spring scale straight up? Is it 75, 75? Right? It would be, right? So it'd be 75, 75. Okay. If you take that angle between them all the way to 120 degrees, well, we just found that. We've got 150 newtons in each one. Okay, so it went from 75 newtons to 150 newtons. Okay. What if you make it closer to T-shape? Can you ever make a perfect T? No, you can pull with like a billion newtons in each direction, and it still won't exactly make a perfect T because there's always this vertical components going on too. Okay? All right. So it looks like this 90 degree angle would be somewhere between the 0 degrees and the 120 degrees. So I think the force in each one is going to be somewhere between 75 newtons and 150 newtons. You guys think so too? I think the answer to part B is going to be somewhere between 75 and 150 newtons. Right? So let's do pretty much exactly what we just did. Do the same thing. Here, cross this aside, try this out. So 98 part B, okay, a Cartesian system. Right, here's where everything comes together. There you go, 45 degrees off this way, 45 degrees off this. Or I meant to ask you guys, right? What's here, if it's 90 degrees between them, what's half of that like to the vertical line? But you guys would have said, but that's what we call that 45 degrees right there, right? That's what I said. Okay. And I've also got this 150 Newton weight still pulling down. mg still is 150 newtons, like that. Okay. Here, if that's 45 degrees, what's this angle right here? 45 degrees. Okay. Let's go ahead and split this in components. One nice thing about 45-degree angles is if you somehow made the mistake of switching sine and cosine or pick the wrong one, you would still get the correct answer because sine of 45 degrees and cosine of 45 degrees, that's the same thing. Okay? Or if you like, you can think of it like here's right, up, here's left, up. Okay? This angle is also 45 degrees. It's a 45, 45, 90 triangle, right? So opposite of that 45 degrees is adjacent to this 45 degrees. Okay. Anyway, here, suppose I play out this angle right here. That's what I'm going to do. Oh, I need to label this F sub T, tension force. This one's also F sub T, tension force. Right? I mean, if we're allowed to know that they're the same because of symmetry or something like that. Okay. And here, I'm going to write down this prediction. I'm going to guess that this tension force is greater than 75 newtons, because it would be 75 newtons if they were both pulling straight up. But it's less than 150 newtons, because I remember when you expand this angle even more, it goes up to 150. So this one has to be somewhere between there. Okay. Maybe I'll guess, 100 newtons. I'm going to guess. Okay. So that when we get an answer at the end, we check, like, does this answer seem reasonable? Right. I'm hoping it's kind of close to 100 newtons. Right. We about to find out. Let's do the same method that we just did. So the sum of the forces horizontally has to go to 0, and then vertically the same story, but let's start with that one. So this would be ft cosine of 45 degrees. This is ft cosine 45 degrees, ft sine 45 degrees, ft sine 45 degrees. Okay, feel like that? Okay. So horizontally, I'm gonna say this guy here, ft cosine 45 degrees minus this guy to the left, ft cosine 45 degrees is equal to 0. Okay. Just like before, maybe you guys predicted that was going to happen. Looks like a dead end. Just whatever tension you plug in would satisfy that. Right? Maybe at best it could confirm that it is the same value. Right? So call it F left and F right. I could just put, okay. At least I know F left is equal to F right. Okay. But other than that, it's kind of a dead end. So let's go look vertical. Let's see what's going on vertically. Sum of forces in the vertical direction. Still 0, still equilibrium. Okay. So now I got this and this up versus this down. Okay. So let's call that ft sine 45 degrees plus another ft sine 45 degrees minus 150 newtons goes to 0 newtons per equilibrium. So for what is the tension force? Does anybody have memorized? Does anybody know what is sine of 45 degrees as a fraction? It's like root 2 over 2, or like 0.707, I think, something like that. Okay. So I got root 2 over 2 of the tension force plus another root 2 over 2 of the tension force. Here, I'll add the 150 newtons over. So that's equal to 150 newtons. Right, like that. Ooh, half of something plus itself. I think it's just going to be root 2 times the tension force is 150 newtons. So the tension force is 150 newtons divided by the root 2. The tension force is, say, It better be between 75 and 150 newtons. If it isn't, then something's messed up. 150 divided by the root 2. Hey, 106 newtons. 106 newtons. Look at that. That does look reasonable, so I am happy with that. Right? Because if it's a pattern, thinking, well, what happens when you change that angle? What's the dynamics there? What happened to in your lab a week or two back? Yeah, it all lines up. Okay. Okay, you guys got that? All right. Let's see what's next here. Number 90. Number 90. If you use a horizontal force 30 newtons to slide 12 kilogram wooden crate across the floor at constant velocity, what's the coefficient of kinetic friction between the crate and the floor? Okay. So they gave us an applied force. They told us how much, and they told us the mass of the cart. They also said constant velocity. Guys, constant velocity, let's go through the process. What's the acceleration equal to? 0. Therefore, what is the net force equal to? 0. Boom. That's that guy right there, isn't it? Right. That is the free body diagram for exactly the question we're looking at. Right. So they told you the mass of the box, so you could probably very quickly get the weight. Oh, and the weight better be balanced out by the normal force, because zero net force vertically. Right? They told you the force you're pulling with, but they also said constant velocity, which means you also know what the friction force is. It better be balancing out the pulling force, right? So these two are equal and opposite. These two are equal and opposite, right? Not because of Newton's third law, but because of equilibrium. Okay. Quick review. I think we got a minute here. Okay. Do you guys remember what is Newton's third law? Equal and opposite force to the Earth pulling down on the block. And it's not the normal force. It's the block doing what? Pulling up on the entire Earth, right? Okay. Similar story for this normal force, right? So the block and the surface are pushing against each other. Not necessarily equal to the weight, because it could be like in an accelerating elevator, in which case it'd be different. But, hey, so side thought there. Let's just redraw that free body diagram and apply the numbers to it. For this is number 90. This is number 90. So they said the mass is 12 kilograms. Okay. Here. Vector. Okay. So, guys, how much is the weight? Is that 120 newtons about? Pretty close to? Okay. What do you guys think the normal force is equal to? Yeah, 120 newtons. To satisfy this condition, sum of the forces in the y goes to 0 newtons. Now, the other condition is the sum of the forces in the x direction also goes to 0 because constant velocity. Okay. So they said F pull was 30 newtons. I'm trying to make my vectors approximately to scale. They're exactly, they're kind of close, right? Therefore, the friction force must also be 30 newtons, right? This was half of your guys' friction lab. This was the first half of your friction lab. Whatever the spring scale was reading when you were pulling that block across, must also represent the friction force as long as you pull at constant velocity, right? As long as you pull at constant velocity. Like that. Okay. So finally, the actual question though is what is the coefficient of kinetic friction? And you guys know that's, well, that's just comparing these two forces. What is the friction force compared to the normal force, right? Which is also a material property. Like once you know what materials you're working with, right? Like suppose I got like this black paint across this paper surface, right? That is some value that would apply to those materials. Right? So in this case, we got friction force was 30 newtons. The normal force is 120 newtons, right? And we only know that because, well, okay, we know what the pulling force and the weight are, so they must be those values. Does that look like 0.25 or like 1/4, right? So what I'm saying here is the friction force is going to be 1/4 of the normal force. That will always be true for those surfaces if they're sliding past each other at constant velocity, right? Or you could just experiment to calculate what is coefficient of kinetic friction, right? And then in that case, you could determine what material it is. Like looking at this list, it's kind of close to this. I bet there's different kinds of wood. This is probably kind of a round average, right? So maybe it's some kind of wood against some kind of wood, for example. Maybe something wood against paper. I don't know, maybe something like that. Yeah. This is one of the very few times in this class you guys get to write a number that doesn't have a unit attached to it. Or if you want a unit, you could say that's Newton per Newton. But you just leave it as 0.25. And yeah, look at that. All right. Here's our pause point for today. That one's going on Google Classroom right there.